Let us start this lecture with a thought process basically about entropy. Entropy is a non-conserved property based on Clausius inequality. Unlike the widely used term energy, entropy provides a measure of disorderedness of matter that with time increases to lead a decent and effective life. By organizing our work in proper line, one can follow the path of least entropy by consuming in our life least energy. So, if you look at the last lecture, we basically discuss about the Clausius inequality, which will be useful for a cyclic operating device, right. But in the real situation, we need to what you call use for the non-cyclic processes. We will have to do the similar we have done for the first law of thermodynamics. We will take a cyclic process, and let us say the cyclic process, process moves from state 1 to the state 2 through the path A, and it comes back from state 2 the state 1 through the path B, and this is let us say reversible, right. And similarly, we can say that this is also there is another cyclic, I mean between the state 2, one can think of the 1 A 2 C and 1, there is another cycle. So, now we can basically apply the Clausius inequality for the 2 cycle, that is 1 A 2 B 1 and 1 A 2 C 1. Right. If you do that, what we will get? We will guess basically the we know the cyclic by the Clausius inequality, the cycle integral of the dq by t is equal to 0, because it is a reversible process, right. And that is what? That is basically dq by t for the path A 1 A 2 plus the dq by t for the path 2 B 1 is equal to 0. And if we take for the other cycle, that is 1 A 2 C 1, I mean if we decompose this path, that is basically dq by t for the path 1 A 2 plus the dq by t for path 2 C 1 is equal to 0. Now, if we just if we subtract this one, right, what we will get? We will get I mean if we just subtract this one, so this will be cancel it out, and this is minus, right. So, what we will say? We will say that basically that is dq by t for path 2 B 1 is equal to dq by t for the path 2 C 1. What it indicates that that the dq by t is basically independent of the path, because as we have just now seen that for the 2 different paths, that is 2 B 1 and 2 C 1, dq by t is same, right. So, this is a we can call is basically a property, and that we will be considering as a property, because it is a point function, it does not depend on the path, and that is nothing but what we call entropy change, or the like that is nothing but ds is equal to dq by t. If you recall, we did in the similar way, we have defined the internal energy for the first law of thermodynamics, and we are defining the entropy by using the second law of thermodynamics, right. So, here what we have done? We have used the Clausius inequality and also shown that the second law of thermodynamics leads to the property of a system known as entropy, right. So, by that way, and we can really define what you call the entropy change. and then we can say that ds2 by ds1 is equal to dq by 2 for the reversible, right, path. So, this is your basically reversible path from state 1 to the state 2, and this also can move like from 1 to 2 in a irreversible path, like I have shown it as a dashed line. And dq by t can be integrated along the internally reversible path to give the value of entropy change. We have already seen that is basically S2 minus S1 is equal to the dq by dq by t for the reversible process is equal to the change in internal and change in entropy for the irreversible process. Keep in mind, this is basically irreversible process. Right. That means we can find out the entropy change for an irreversible process between two states by considering at a reversible process. In other words, you can substitute an irreversible process, right, with an internally reversible process, right, and so far the state is same, so therefore entropy change will be same. So, in other words, change in entropy for an irreversible process determined very easily by dividing suitable imaginary reversible process between two states. And let us look at entropy change for a certain process, like we know that change in entropy is equal to dq by t for reversible process only, and as I stated earlier that entropy is a state function. So, the entropy change is dependent only on its initial and final state. It does not depend on the path taken by the system whenever it is interacting with surrounding. Basically it is a independent of the path, but it is dependent on the what you call state or the point between which the system undergoes the changes. So, by analyzing the irreversible process, right, in other words, what you call like for analyzing irreversible process, right, we need to substitute this irreversible process by imaginary equivalent reversible process, and such that we can calculate the entropy change between two states whenever system is interacting with its surrounding. So, for that we will have to do, I am just restating the same thing. Let us look at the entropy change for a heat interaction. So, let us take an example, that is temperature of a large reservoir remains almost constant at 350 Kelvin when a paddle wheel is rotated for 1 hour by using a 125 watt motor, and we need to estimate the change in entropy of the reservoir if the paddle wheel is operated in a very slow manner, so that it will be, one can think of reversible kind of things. So, if you look at, this is our system, I mean the thermal reservoir, and which is at 350, and you are giving some 125 watt, it is a very big reservoir, so that there is not much change in the temperature, and you are using a motor for that. And of course, you can consider that it is an irreversible process. Why? Because you cannot take it, whatever the work being done on this, you cannot really produce again to the if this work is being done on this thermal reservoir, and that same amount of work cannot be make the motor to run, if you consider like other way around. So, therefore, it is an irreversible process, but we can consider that a imaginary reversible process, and that is this whatever the work you are giving is equivalent to the some heat energy during the reversible process dq, and therefore, the change in entropy will be dq by T for the reversible process. In this case, the what is the dq R is nothing but the work done. Work done is 125 what you call watt, and that is run for the 1 hour, right. And if you look at this is of course 125 watt, but here I have taken the kilowatt. So, therefore, it will be 3600, right, 1 hour kind of seconds. So, they divide by 350 will be giving to 1.29 kilojoule per Kelvin, right. So, that will give the entropy change for this thermal reservoir. Although it is an irreversible process, we have considered that as a reversible process, considering that work is converted into heat, and then you can and done in such a that there is no change in temperature of the thermal reservoir, then we can estimate. So, if you look at the heating or cooling of the matter is basically is an irreversible process, and the irreversible process can be considered as a basically imaginary reversible process between state 1 and to 2. Like if you consider, let us say, between a process, let us say this is PV and this is one process like which is state going to 1 to 2, but I can consider is as a some imaginary process, like I can say this is constant pressure, and then it can be what you call a constant volume process, and it can go to the constant pressure process, like you can, and you can say this is A, this is your isobaric process which is reversible, and this is isochoric process, reversible, right, reversible isochoric process. So, heating and cooling is can be considered as a basically isobaric and isochoric process, and as to the first law of thermodynamics, we know that dq is equal to du for the isochoric process, right, and for isobaric process dq is equal to dh, we have already learnt. So, for isobaric process we can find out the entropy change is nothing but your dq by T, and which is nothing but your change in this dq is equal to, because dq is, we know that dq is equal to dh. So, therefore, that will be mCp dt, and we will take Cp is not really function of temperature for this thing. So, or you can assume as average Cp, so that if we integrate this thing we will get mCp ln T2 by T1, right. That is, you are considering that as a reversible process, and you are finding out the entropy change. Similarly, for the isochoric process you can have dq by T, and then we know that dq for isochoric process is nothing but your what you call equal to du, and that is mCv dt, and then divided by T will give, when you integrate it, will be mCv ln T2 by T1. Keep in mind that this we are saying that Cv is constant, it is not a function of temperature. So, by this process you can find out the entropy change for what you call for the isochoric process and isobaric process. And let us take an example that we need to find out the entropy change if 1 kg of water at 30 degrees Celsius is heated to 80 degree Celsius at 10 power to 5 pascals, and the Cp of water is given. So, what we will do, we will basically find out that ds is equal to dq by t, and that we have seen this is a what you call, we can consider that this process is isobaric process because there is no change in pressure, right, and then that is dq is equal to dh, and that is nothing but Cp dt, because we can consider this is 1 kg. So, mass is basically 1 kg, in this case mass is 1 kg. So, mass is will not consider. So, that is Cp ln T2 by T2, and Cp is given to you. So, therefore, that will be what you call 4.2 into 10 power to 3, this is kilojoule, therefore, I have taken this ln 273 divided by 80 and 80 degree, because you will have to use the Kelvin and 30 degree. So, you will get this is basically change in entropy is 0.6415 kilojoule per kg Kelvin, and you can consider this as a basically per unit mass kind of thing. So, I could have used this as a small s, small s. This is nothing but a small s we use per unit mass, right. And if you want to find out basically this thing, that change in entropy, that is nothing but your delta S will be 0.6415 kilojoule per Kelvin. That is your, because mass is given 1 kg, so you just multiply and it will get. So, let us say that like we need to find out entropy change for an ideal gas, and which is going from state 1, which is at P1 V1 T1 to P2 V2 T2. Let us say that we are having this point, what you call state 1 here and state 2 here, like this is, we can say that it is an irreversible process, right, and we need to find out entropy between the state 1 and state 2. So, how to go about it? And this state of course, I have already told you that is P1 V1 and T1, and state 2 is your P2 V2 T2, right. So, how we will go about it? Basically, what we will do, we will have to substitute this imaginary substitute this irreversible path by certain reversible path, right. For example, I can say that these are the two isotherms, right. One is temperature T2, other is T1, and I can say that this is basically path is one is, we are saying this imaginary path, the irreversible path between state 1 and state 2 can be considered like substituted by two reversible path. One is isobaric, that is 1 to A, and then it will go with the again reversible isothermal to the state 2, right. I can do that, I mean like, because so far entropy calculation is concerned, I can substitute these two things. So, and similar way I can say there is another one which is between state 1 and it can be, I mean also the same thing, because the entropy change between state 1 and state 2 will be not dependent on the path, whether this path, let us say if I say this is this path or this path, and again this between that I can say that it will be having two what you call path, we are saying it can take place. One is isochoric path, that is what you call here, and then it will return back to the state 2 with the isothermal, reversible isothermal process, and this also reversible isochoric, right. So, we can estimate by this way that entropy change between state 1 and state 2. At this point we are calling it as a B, right. So, what we will do, for the path 1A, right, that is your 1A 2, right, this path which is nothing but your between entropy change between the state 1 to 2 consists of isobaric 1A and isothermal A2, both are reversible. Okay. So, for the change in entropy for the path 1A is equal to dq by t, and this is the isochoric process. Therefore, dq is equal to dh, and dq is equal to dh because it is isobaric process. So, dq is equal to dh, and dh is nothing but your Cp dt is equal to Cp and dt, right. So, I will put it here, and when you say that Cp is constant, so therefore, when you integrate it between 1 to 2, I will get Cp ln T2 by T1. Is it fine? So, similar way we can find out the entropy change between the path A to 2, right, that is nothing but dq divided by T, and we know that for the isothermal process that is du plus Pdv, and for isothermal temperature is not changing. So, therefore, this will be 0, right, and that is nothing but P dV by T, and we can integrate between the state 1 to 2, and this is an ideal gas, So, therefore, I can write down R ln V2 by Va. Can I not write down, because in this case I can use the ideal gas law, that is what you call R divided by dV, right, this is equal to R divided by V, and then you integrate it here, and then you will get R ln V2 by Va. Now, we need to connect this volume at A station A to volume at station 2, right. How we will do that? We will have to use the ideal gas law, that is P2 V2 is equal to PA VA, and PA is nothing but your P1, the pressure at A, because this is isobaric process. So, is equal to PA is equal to P1, and therefore, we can write down V2 by VA is equal to P1 by P2. So, if you add this thing, then we can get the change in entropy for the A22 for the path A2 is equal to minus R ln P2 by P1. Keep in mind that we are just changing the ratio, therefore, minus sign comes over. So, when you add this thing, put these values here, like change in entropy between state 1 to 2 is equal to entropy change for the path 1A plus entropy change for path A2, right. When you substitute these values, you will get an expression here, that is change in entropy between state 1 to 2 is equal to Cp ln T2 by T1 minus R ln P2 by P1, right. So, you can now evaluate for the what you call the entropy change for an, of course, an ideal gas that we have considered here by substituting the irreversible process between state 1 to 2 with reversible isobaric followed by the isothermal process. In this case, we have seen. And let us consider the other way around, that is for the path 1B2, the change in entropy is equal to isobaric process for path 1, isochoric process for the path 1B plus the isothermal process B2, right. So, what we will do? We will do evaluate them similar way. The change in entropy for 1B is nothing but dq by dt, and this for isochoric process, what it would be? It will be change in internal energy, and that is nothing but your Cv dt by T, and when we integrate it between station 1 to B, isn't it? That is Cv ln T1 Cv ln T2 by T1, because why it is Tb is equal to T2, right. So, for the path B2, the change in entropy will be equal to basically du plus Pdv, that is nothing but dq by T, and in this case that is what you call isothermal process, therefore, that will be 0, and using ideal gas law we can find out that is nothing but your Pdv by T. When you integrate, I mean, like you can substitute this by the what you call Pt is equal to R by V, and then integrate that thing is R ln V2 by V1. So, you can add all these things together, you will find out that that is basically change in entropy is equal to Cv ln T2 by T1 plus R ln V2 by V1. Keep in mind that this is basically integrated, this B2 is integrated between B2 to 2, B to 2, and Vb is equal to V1, right. Vb, this is Vb is equal to V1, right. So, we will get an expression, you know, we have already seen that this is for the expression for which is in terms of Cv, and of course, the ln T2 by T1 and R ln V2 by V1, and equation 1 which we had derived earlier for the isobaric process followed by the reversible isothermal process are you know are in terms of Cp and ln T2 by T1 minus R ln P2 by P1. So, these equation 2 are different. Is it different? Can it be? Or it will be same, right. I think I will leave that an exercise for you to prove that equation 1 is equal to equation 2. In principle, it should be. Now, I will leave that an assignment for you people to do that. So, entropy change for a pure substance we need to evaluate for our problem, because you know, like entropy is a property we know, thus the value of entropy is basically dependent on the state of the system, and once it is state of the system is fixed, so there it can be, you know, fixed. For example, like, you know, if you look at like this is the TS diagram, if you look at this is your compressed liquid, right, and for the compressed liquid what you will do, if you know the P1 and T1 from the saturated steam table corresponding to the saturated liquid point, you can find out SF, you know, that is the liquid is equal to S1, you can find out very easily. And similarly for the superheated steam or the superheated vapor, it can be steam, it can be refrigerant also, right. So, you can find out basically at a particular pressure, that is let us say P3 and T3, you can evaluate S3 from the superheated steam table or the refrigerant table, right. But if the mixture is in between, like it will be some different quality, right. So, you need to know this quality, and then if you know the entropy at the saturated liquid point, and if you know the change in entropy between the saturated vapor point and the liquid point, then you can evaluate what will be entropy, provided you know the what you call either temperature or the pressure, any one of them saturated condition, and also the quality. So, if you look at, like let us say there is the what you call sublimation, that means the let us say there is a ice which is converted into liquid, then change in entropy will be heat of sublimation divided by the temperature at which the sublimation occurs, right. Similarly, for the vaporization, you can find out change in entropy is basically heat of vaporization divided by the temperature at which vaporization occurs. So, we will take a very simple example like 500 grams of ice is melted to water at 0 degree Celsius by heating it slowly, right, by heating it slowly, and we need to determine the entropy change. So, what we will do, we will have to change in this entropy during this melting process is equal to HSF divided by TSF. HSF will be given in a table and which happens to be 333.4 kilojoule per kg, right, and then you will use the temperature, it is occurring at 0 degree Celsius. So, the in Kelvin that will be 270.15, and you know these grams, and then you will get the if you substitute these values you will get 0.6 kilojoule per Kelvin, that is the entropy change during this melting of ice. So, we will have to now look at basically entropy change for an irreversible process, right, and we will have to see how we can handle. We can take a control mass system which undergoes a reversible cycle 1A, what you call 1A 2B1, this is a reversible cycle, right, and we will consider for that we will apply this what you call Clausius inequality, which is equal to that 1 equal to dq by t for the path 1A2 plus dq by t for the path 2B1 is equal to 0, right, for this path. And we will take an irreversible cycle, that is basically I can represent this as a dash line, this is basically a dash line, and then that will be the path is what you call the cycle is 1A 2C1, right, and we can apply the Clausius inequality, and that is dq by t for the path 1A2 plus the dq by t for the path 2C1, which is irreversible path. Of course, this is the same the reversible path. So, that cycle become irreversible. Any one of the path is irreversible means cycle will be irreversible. So, what we will do, we will just subtract this one, right, and if we subtract this one, that what will happen, like if I subtract this one, this is minus and this will be cancel it out. So, you will get dq by t for the path 2B1 minus dq by t for the path 2C1 is greater than 0, right. And what it says that dq by t for the path 2B1 is basically greater than the dq by t for path 2C1, right, that is the change in entropy. So, as the process 2B1 is reversible, right. So, therefore, the change in entropy for the path what you call 1 to 2 is greater than the dq by t for the path 2C1, right. We are just restating because this is reversible, so therefore, I can say dq by t nothing but your entropy change. In general, we can write down the change in entropy is basically greater than dq by t for the an irreversible cycle or irreversible process, right, and the equal to dq by t for the reversible process. So, we can basically say that this is a generalized equation, that is ds is equal to dq by t for the reversible process and change in entropy is greater than the dq by t for an irreversible process. For an isolated system, right, we can say that dq is equal to 0. From this relationship we can say that ds change in entropy will be greater than equal to 0, right, for an isolated process. That means there will not be any what you call energy interaction, and also there will not be any what you call heat interactions, right. So, that is an isolated system. So, therefore, entropy of an isolated system increases or remains constant, right. But in if you look at first law of thermodynamics, we have seen the energy of an isolated system can, what will happen? In case of an isolated system, energy is conserved. In this case, need not to be, right. Entropy is not a conserved property. So, the process can never occur in the direction of decreasing entropy. So, then we can say that whenever there is a entropy change is equal to 0, the process is reversible, and if the entropy change is greater than 0, it is an irreversible process, right. So, this is basically known as the principle of entropy increase. That means, entropy of the, if you look at the an isolated system always may be increased, or it may remain constant, but it cannot really decrease. If it is not, if it is, it cannot never be, will be less than that. So, this principle is a very important one, like which will be says, and people says also the entropy of the what you call whole universe is increasing all the time. So, when change in entropy is less than 0, that means the process is impossible. It is not possible to have a process where the entropy will be less than, because it is violating the principle of entropy increase. So, for an irreversible process which is operated for the same dq and t, then we know that ds is greater than dq by t, right. So, what we can say, we can write down ds is equal to dq by t plus hg, and this hg is nothing but entropy generation, that is for an irreversible process. And for reversible process, what will be this hg? What will be this hg? Hg will be 0 for a reversible process, and this irreversibilities is basically being caused either due to friction or mixing or unrestrained expansion or heat addition, with a finite temperature difference. Temperature gradient is more, the irreversibility will be more, but we have seen that quasi static state where the gradient is very very small, you can call it as an irreversible process, right, which you can call it as a reversible process if the gradient is infinitesimally small. So, as I told that Sg is greater than equal to 0 and Sg is equal to 0 for a reversible process, and Sg is greater than 0 for an irreversible process. And the value of Sg is always positive quantity, or it will be 0. So, question then arises, we have learned that entropy is a basically property of the system, right, yes or no. Now, is this Sg a property of a system? Can it be? Actually it cannot be, okay, because it is dependent on the path what it will be taking. So, therefore, it cannot be a property of the system, that is the entropy generation. So, how do we use the principle of entropy increase for a non-adiabatic system? Because what we have seen is basically we are saying okay, dq is equal to 0, then we talk about it, but how we will do that? So, what we will do, as I told that entropy is an extensive property, hence it is additive in nature, right. So, therefore, if I say that isolated system, right, if I take an isolated system, that means there is no energy or the interaction, and it may have subsystems, like let us say subsystem 1, 2 or 3, it may be n number of subsystems, then total entropy change is basically summation of entropy change for the each subsystem will be greater than equal to 0, right. Then if you know that, I mean one can really find it out. Let us consider another example. There is a system, right. If I consider this contains some, let us say gas, and then it is interacting with the surrounding, both the work or the heat interaction will be taking place, right. And I want to find out what will be the entropy change between the system and the surrounding, right. I do not know like what is happening. What we will do, we will take this as a surrounding here, what I have shown here, this is basically surrounding, and then put together this is an isolated system. That means if I consider this as my system boundary, right, in this case Q and W, in this case, right, the Q is equal to 0, W is equal to 0, but the system is embedded inside the surrounding. I am taking both the system and surrounding as a isolated system, and if you do that, then you can easily calculate what will be the entropy change, and then one can do that. So we can say the total entropy for an isolated system will be change in entropy of the system plus surrounding will be greater than equal to 0, right. And if I know this what is happening system, and if I know that what will be the, then we can find out what will be the surrounding, right, kind of things, and then we can evaluate. And this concept is being used, if you look at isolated system, is being used very often to calculate the entropy change, where you can certain things are not known. So the entropy change, if we look at as I told, basically for a isolated system we will be considering both system and surrounding greater than 0, and this is the general expression for the increase of entropy principle. And if I consider that same, I am saying that there is an entropy change is in the system, right, and that is minus kilojoule per Kelvin, and this is your surrounding, right. This is your surrounding basically, whole this thing, and the entropy change for the surrounding in 5 kilojoule per Kelvin. So in this case, what is that, system entropy is less than 0, right, in this example, and change in entropy is greater than 0. So total entropy, what it would be? Total entropy will be basically will be greater than 0, because if we add together what will be? It will be change total entropy in this case, when you add in this example, the total will be equal to 1 kilojoule Kelvin, which is greater than 0, right. So therefore that indicates that the increase of entropy principle. So if you just say that if the total entropy is equal to 0, then we call it as a reversible process, and if we say total entropy is equal to greater than 0, it is a irreversible process. If it is total entropy is less than 0, it is impossible process. Hence the second law of thermodynamics indicates the what you call direction or the feasibility of process. That means whether the process is possible or not, it stipulates, right. So I think this is the way what we can think of applying the what you call entropy increase principle for calculating the various entropy and then find out whether the process is possible or not. And I will just tell you basically quality of energy. By that, can you say that from this whether the what is the quality of energy? For example, if I take the certain amount of heat is being taken from what you call the source at temperature Th, and then it rejects this heat engine reject the QL amount of heat to the temperature 300 Kelvin, of course producing W amount of heat. And keep in mind, this is basically a reversible heat engine. Now, and if I so now question arises, how do we can increase the thermal efficiency of this Carnot heat engine? You will consider reversible heat engine, basically Carnot engine, and how about the actual heat engine? What is the way of means of doing that, right? If I look at, I will take some example. For example, we know that Carnot efficiency is equal to 1 minus TL by TH, right? And if I take this what you call TH as 1200 Kelvin, and of course the low temperature is 300 Kelvin, that is the sink, what will be efficiency? Efficiency is basically 75% for a Carnot engine. If I take the 900 instead of 1200, if I take 900, it is 66.6. If I take 600 Kelvin, right, it will be 50%, right. What is we can infer from this? That means if I am taking the higher source temperature, I am getting higher efficiency for the same sink temperature, right. That is from the Carnot cycle, and that will be true for the other irreversible engine as well, because this is an irreversible engine. And suppose I will say that now there is a heat engine where you will have to change the sink temperature by delta T, let us say, and you will also experiment and change the temperature, source temperature as by delta T. If you look at efficiency wise, in which case it will be higher? What I will suggest that you please look at this problem, and I am giving this as an assignment so that you can check which one will be higher, which one will be lower, and why it is so. But from this example, if you look at what we are learning from here, that means if the heat energy available at a higher temperature, then its quality will be higher as compared to the energy which is available at the lower temperature. That means if you look at quality of the things will be goes on increasing with the increasing of the temperature at which thermal energy is available, right. So, we will be coming back to this quality of energy little later on, whenever we will be talking about the availability and other things. So, we will stop over here. We have learned basically that how we have used the entropy increase principle to evaluate the entropy for the not only for the reversible process, but also for an irreversible process, right. And we now equipped with a tool for what we call estimating the entropy change and also the predicting whether this process is possible or not. So, if you look at the first law of thermodynamics is basically talk about the quantity, it will give you quantitative evaluation and the quality of the energy being stipulated by the second law of thermodynamics, that we have also learned. Thank you very much. I will stop over here.